For those of you who have kind of seen me do this talk, by the way, my name is Yves. I'm with VMware. Typically, I do this talk alone, but this time I thought I'm going to be allowing myself to kind of be joined by this wonderful human being.
Hi all, my name is Daniel Sutov. I'm a technical architect with Equinix, and we're doing this, well, together, for you to learn some NSX today.
Thanks, Daniel. So we're going to kick this off. Of course, there is the disclaimer, although I don't think we've got any kind of functionality described in here which kind of is looking to forward-looking things. So should be fine. So I'm going to be talking about, let's say, a very small recap what NSX is all about, talking about how to build logical topologies with NSX, and then some general design guidelines. So I'm kind of setting the frame, and then Daniel is going to take over and walk us through some very specific things that are important for service providers to kind of use those rules that I've actually laid out in the beginning. So brief recap of NSX. I would argue most of you probably know what NSX is all about, but the main idea is that we somehow decouple ourselves from the physical infrastructure. So in this case, you see a couple of VMs on the slide, and obviously, we would like to organize those VMs in a logical topology as such. So a couple of VMs on logical segments, routing between those segments, maybe internet access through a firewall. So how do we do this while we still have, let's say, physical networking associated with the place of where those VMs are? So in comes the overlay. So effectively, what we do with NSX is that we put so-called tunnel endpoints on every ESXi host, and we have a central control plane that takes care of finding out the MAC addresses and the IP addresses of every virtual machine and associating them basically with the host that they're on, such that if you ask the control plane, where is this VM, because I want to communicate with that VM, effectively the control plane will answer with the tunnel endpoint IP address, which allows the ESXi host to build a tunnel from the ingress host to the egress host. So effectively, if VM1 wants to talk to VM2, the host number 1 will encapsulate that packet into a so-called Geneve tunnel. It doesn't really matter whether it's Geneve or pigeons or any kind of other tunneling mechanisms, but we are using Geneve inside NSX, as that's the only IATF standardized tunneling mechanism for overlays. Of course, NSX does way more than that. Effectively, NSX also allows you to put a default gateway on every ESXi host. And it doesn't really matter where the VM is. It can go to any kind of ESXi host in the environment. It will always find the same default gateway. So that takes care of routing. It also does things like load balancing, firewalling, together with intrusion detection, prevention, network detection and response, gateway firewalling, NAT, DHCP services, and a whole lot more. So the way that NSX is productized is we have the central control plane that I already mentioned before. It's a set of 3 nodes that you deploy in your vSphere environment. They cluster together, so they kind of have both the notion of achieving redundancy between those control plane nodes, because we have a 2+1 redundancy, so we can fail one node. But we also load share all of the information that is needed to store inside the control plane across those 3 individual nodes. Some people ask me, do I need more than 3? In typical environments, and for sure to the notions that NSX is scaling, we don't need more than 3. As a matter of fact, the only supported number is 3 control plane nodes. Then those control plane nodes can also talk to other NSXT instances. That's through what we call federation. We'll talk more about that later. And then they connect to the data plane. The data plane, for the most part, is going to be on ESXi hosts. So we call those transport nodes. And NSX basically takes the VDS as you know it and turns it into a VDS plus. So it adds routing capabilities, it adds firewalling capabilities, it adds tunneling capabilities, and so on. And they connect to both the management plane as well as the control plane on those ESXi transport nodes. There's a special transport node that we call the NSX Edge node. More on that later, but essentially it's kind of like a bucket of routing functionality. And as a matter of fact, one NSXT Edge node can hold hundreds of different kind of entities of routing. More on that later. Those transport nodes can be deployed in in a bare metal form factor. So we give you an ISO, you turn a server into an edge node, or you can also just deploy a VM, an edge node as a VM, but as a matter of fact, the functionality is exactly the same. We also leverage DPDK forwarding, which is essentially a way of doing fast switching. If you know about Cisco times, I mean, fast switching was this methodology of kind of doing fast switching, as the name implies. With DPDK, we can do very fast forwarding on the ESXi, so on the NSX edge transport nodes. Obviously, we also need to support containerized workloads. We do this through kind of a layer of additional data plane, which we refer to as Antria. So Antria is the ability for containerized workloads, which are running in Kubernetes nodes, worker nodes, to talk to one another, to enforce policies, and so on. And the good thing is that the Antria, although that's a totally separate control plane and data plane for containerized workloads, we can actually manage the Antria state through the NSX manager as well. So that's a very short two-slide recap of NSX. There's probably way more discussion about NSX ongoing in this show, so I would encourage you to also kind of take a look. If you want to know more, take a look at those other presentations. So let's talk about logical topologies now. So again, NSX allows you to create a logical, i.e. it's not a physical topology, it's logical totally. So in this example, we have two segments. And by the way, these segments, again, they can live anywhere. They're kind of really logical segments. They're not like a VLAN. They're so-called overlays. We have a couple of VMs attached to them, the green segment, the blue segment. We would like to route between those two segments. And also, we want to connect the logical gateway to the physical network as well, because just doing NSX in a little bubble doesn't make any sense. So if you now take the physical look, again, those VMs are represented there. So you can see we connect the ESXi host, obviously, to a switch fabric of some sort, typically leaf spine. If you want to kind of establish routing between the segment 1 and segment 2, we do this by virtue of kind of somehow exploding this green router into multiple different components. One of the components is the distributed router component. And as a matter of fact, every ESXi host has one DR, or distributed router component, of that same logical router. So if you have one logical router, and you have, in this case, 8 ESXi hosts, you have 8 DR components running in the environment. But they are all part of the same logical router. This means that if you want to route between the blue and the green VM, effectively, that hypervisor itself would take care of the routing. So the hypervisor takes the packet, routes the packet, which is nothing else than swapping some MAC addresses, decrementing time to live, and then tunnels the packet on the destination subnet to the destination host where the green VM resides. On the other hand, logical router also contains a service routing component. And a service routing component is needed if you want to, for example, connect to the physical domain. So in this case, if the green VM wants to talk to some entity in the physical network, the NSX can basically take care of this by encapsulating that traffic again, send it to the NSX edge node, where it finds the service routing component, again, of the same logical router, and then effectively switches this to typically an uplink, a VLAN, such that it can actually reach the physical domain. So again, I want to kind of stress this. Every logical gateway in NSX is comprised of typically at least one SR component and multiple DR components, as much as there are ESXi hosts. We've also kind of decoupled, or we are tiered the logical gateways as well. We have so-called tier 1 gateways, and we have tier 0 gateways. And the idea is that the tier 0s are going to be typically installed or provided by the service provider or by the operator of the network, whereas the tier 1 logical gateways can be consumed by the tenants themselves inside the environment. So we have like this kind of layer in between of operationals and of ownership of those objects inside NSX. By the way, the connectivity between the tier 1 and tier 0 is totally automated. You basically just say, this tier 1 wants to connect to this tier 0, and effectively all the networking in between and the subnetting is done by NSX automatically. All the routing is plumbed by NSX automatically. Don't need to worry about that. So edge nodes, I've already talked about them a little bit. So every SR component, in this case, let's zoom in on this tier 0 logical router. If we want to effectively enhance the throughput or the bandwidth that this logical router can withstand, we want to connect this logical router with 4 uplinks into the physical domain, such that we can actually leverage the total bandwidth of those servers for physical connectivity. We can effectively distribute the tier 0 across, in this case, 4 different edge nodes. This gives us the advantage we can do equal cost multipathing, in the sense that every tier 1 that is also a logical component will be connected to every edge node in this environment, such that from a tier 1 perspective, it can actually send traffic to 4 different destinations. Therefore, you can increase the traffic capacity. And the same thing for the connectivity between the tier 0 and the physical domain. So again, zooming in on edge nodes, you would typically deploy them on day 0 in your environment. And there are various ways in dealing with how you capacity plan your NSXT edge nodes. One way is that your edge nodes, your tier 0s, are going to be connected, or let's say assigned to given NSXT edge nodes, and you're also going to throw your tier 1s into the same set of edge nodes as well. By the way, we actually group together a set of edge nodes in a so-called NSXT edge cluster. Again, this is done at provisioning time. So in this example, we have 4 tier 0 logical SR components, again, of the same tier 0. And we have, in this case, an active standby pair of tier 1s associated with edge node 1 and edge node 2. We have a standby pair of tier 1s, and in this case, the orange tier 1s in edge node 3 and 4, and so on and so forth. So we can just kind of distribute, let's say, capacity amongst those different edge nodes. So that's one way of doing things. Typically, though, in service provider environments, you probably want to do kind of a bit of a divide and conquer technique, whereby you will reserve one set of edge nodes for your tier 0 SR components, and reserve another set of edge nodes for your tier 1 SR components, and potentially even a third set of edge nodes for bridging, which I'll come to later as well. It allows you to kind of scale your edge clusters in a different way depending on the role of the object that actually resides within the edge node itself. So this is another way you would do this. So in this case, your edge node 1 and 2 would take care of the tier 0 SR component. By the way, one thing which I forgot to mention is that at this moment in time, and I don't think it will change, the design rule is that only one tier 0 SR component can reside in an NSXT edge node. If you want to have more, you need to add more edge nodes in that case. The tier 1s, you can have way more. I think you can have up to 400 tier 1s per NSXT edge node today. And basically what this shows you is that in this case, this edge cluster, you want to scale this for bandwidth, because that connects to the physical domain. Whereas here, you scale for the services, the amount of firewall rules, and so on and so forth that you want to apply to the tenant tier 1 SR components. Now, of course, NSX is very well equipped with, let's say, switching and routing capabilities. And I had to put in one slide at least that talks about security. So you probably heard about distributed firewalling. Effectively, NSX allows you to give every little VNIC a little tiny firewall. Luckily, you don't have to manage every little tiny firewall in the environment. You can manage it centrally. And also, you can manage it using so-called abstract objects. You can say, all VMs in this segment belong to group 1, all VMs in this segment belong to group 2, and group 1 can talk only HTTPS to group 2. So it's very easy to make rules. It's very easy to remove workloads or VMs out of the group or dynamically add them in the group later as well. So we support distributed firewalling on both VLAN segments, also port groups, as well as overlay segments. So Geneve-based segments, we support distributed firewalling. Distributed port groups, we support distributed firewalling. VLAN-based segments in NSX, we support distributed firewalling. On the tier 0 and tier 1 routers, we also support so-called gateway firewalling. And it gives you lots of flexibility in the sense that we also have a thing called a service interface on a logical router, where you can attach a VLAN into a tier 1 and provide firewalling capabilities for that given VLAN. Next to firewalling, we support the entire set of functionality as well. Things like intrusion detection, intrusion prevention, network detection and response. But this would lead us way too far to talk about these features in detail. A fairly new thing that we introduced in NSX is NSX multi-tenancy. So before this feature, if you look at the API, we had essentially an API that started with /infra, and then we had essentially the entire API tree behind it. But essentially, it was a flat structure. And you had to effectively create topologies per tenant to allow or to disallow communication between tenants. So you would give every tenant its own tier 0 or its own tier 0 VRF. And then you would make sure that you wouldn't connect two tenants together. Now, with the NSXT 4.1 release, we introduced multi-tenancy in the sense that we can actually assign the provider admin can now create projects, and a project can be assigned to a project admin. And typically, the project admin would be able to consume or create its own T1s, its own segments, its own firewall rules. And the only thing the project admin can do is attach it to a set of tier 0 or tier 0 VRFs to allow him to communicate with the rest of the world. So different projects can be created. Of course, the enterprise admin can also create a shared services T1 that all projects can also leverage to do things like backups and DNS lookups and so on. Another big thing is that inside logs now, we have also now the ability to assign a project identifier to the logs, which allows you on the syslog server to really kind of look at the different syslogs and see from which tenant do the syslogs come from. And forward those syslogs then also to, for example, the tenant's SIEM infrastructure or their own syslog server. So in terms of connectivity to the physical domain, we have different capabilities. Typically, what you would do is your NSXT edge nodes would run the service routing components of the tier 0s, and they would potentially run T0 VRFs, and every VRF would have one VLAN associated with it, and you would connect the VLAN to the physical domain, and you would allow typically BGP peering between the physical domain and the T0 SRs. But we also have different ways. We can also do, for example, a VXLAN handoff, which is another kind of way of encapsulating traffic. And we would leverage BGP EVPN in this case to exchange type 5 routes. This has the advantage, you only need one BGP session between the physical domain and the NSXT edge nodes. And over that one single BGP session, you would be able to exchange routes for all different VRFs at the same time. And you can also have different tier 0s and connect an overlay between them and run BGP over that overlay. That would be another way of kind of creating hierarchical topologies as well. Another new feature we introduced is the ability to do inter-VRF routing. In this case, for example, we would like to, let's say, route between the blue and red VRFs. We would allow network 20 to be visible on the blue VRF and network 10 to be visible in the red VRF. And we would also like to leak the default route out of the main routing table into both VRFs. So it's a very standard way of basically exchanging routes between different VRFs inside NSX. We used to have this VRF leaking approach before this feature. I would say never use that again. This approach is way better, and it was introduced in the 4.1 release as well. Some other ways of connecting, and I've already alluded to this, is service interfaces. So a service interface is the ability to connect a segment, whether it's VLANs or overlays, directly into the SR component, so bypassing the distributed routing component, which gives you the advantage of the fact that you can now assign, for example, firewall rules or static routes to that given interface. So a service interface is something that is quite important to build things with. But Daniel will talk way more about this than I do. Bridging is another thing that is important. Again, Daniel will talk more about how to use this in practice, but the idea is that you would create an NSXT edge node, you would configure which overlay can be bridged in which VLAN. So some general design guidelines. I'm not going to talk that much about it, but effectively there is a wonderful design guide. I'm going to try to basically kind of explain it on one slide. But the idea is that what you would have is you would have per rack typically 4 VLANs. Those 4 VLANs would be terminated in the top of rack because you would leverage a layer 3 routed switch leaf implementation. And effectively, the extra kind of VLAN you would have to provision for NSX would be this one, the overlay VLAN, such that you can transport those Genève encapsulated packets. Different racks would have different responsibilities. And typically what you would do is your edge node VMs, you typically would deploy them as such, in the sense that you would have different edge node VMs. They have their own VDS. You would have different tunnel endpoints on every uplink, and you would connect those uplinks into a trunk port group on the ESXi host. And that's the typical design that we recommend. And again, this is way too elaborate to kind of talk about in detail. And the other quick thing, because I'm running into, let's say, some of Daniel's time, we have 2 various ways of doing multi-site. One is the so-called multi-site design, whereby effectively we can build one NSX domain, and we can have the ability of allowing the tier 0s and T1 to move over to the recovery side in case the active side would fail. That together with SRM gives you full disaster recovery capabilities. Active also works in the sense that you can have your tier 0 gateways and tier 1 gateways active in both sides, but again, you would have the standby HA components living in the other side in case of failure of one of the sides. So multi-site works well, but of course it has some limitations. You need to have, there are some very stringent limitations in terms of latency or RTT times between sites. Typically, only 10 milliseconds are allowed between locations, so it's really kind of like a per country, let's say, deployment. Whereas federation, which is another feature that we have, has a way larger footprint, but unfortunately, currently we don't support all of the functionality. We don't support VRFs, we don't support multi-tenancy, for example. Recently, we did introduce a cloud director support for federation, which is a pretty cool thing to have. With this, I'd like to move it over to Daniel. Daniel, take it away.
Yeah, will do. Thanks for all the explanations so far. Yeah, let's go for how we can use the design options for NSX, for you all, for service providers. So this is first, I want to show you a timeline of the NSX versions, well, in the the latest ones. So looking at version 3, it was mainly federation that was added as a feature and security ones. So that can be shown here. And as of version 4, like Yves explained, it's pretty much a good focus on multi-tenancy. So as of version 4, it introduced the projects via the API. In 4.1, it was via the GUI, so it made, well, accessible for all of us. 4.1.1 introduced VPCs. And well, the latest one has a couple of additional networking features. So if you look at 4.1, a couple of important ones are the VRF source AS. So now you can have source AS numbers per VRF, in which before it inherited the AS number of your parent. So much more flexibility for now for us as a service provider. Also inter-VRF routing, like Ike mentioned, so good ones in this version. So moving up to the NSX managers, of course we know it's a cluster consists of 3 nodes. So there are pretty much 3 deploy options in this. So the first one is to put them on a stretch cluster. So 3 nodes, put them on the side A, and with standard features, you can move them to the other side. So this is the first one. The second is putting all the individual nodes across 3 sites. So you have 3 of them, and you need to have a load balancer on top of it to access the system. Versus the third one is having 2 active nodes inside A, the third one inside B, and using your replication technique in favor, you can move them over. But it has some caveats, some I will talk you in a bit. So of these 3 options, my favorite would be the stretch cluster. And why? So it involves less complex routing. It has no additional load balancer which can go wrong, so it's more eases your environment. And on top of that, your operations team will have an easier job because you can test the failover easily, and when issues arise, the failover happens automatically, which is a good thing when there are issues. Another one are the appliance sizes for your NSX manager. So the first one to start off for production is the medium one, which can operate up to 128 hosts. And if you plan to go further, use the large one, which has a couple of supports over 1,000 hosts already. Next one is the configuration backup. So that's an important one. So out of the box, it doesn't let you create snapshots on your NSX manager. And you should enable it also. You can do it in advanced configuration, but don't go there. So you cannot backup them using your favorite backup tool or replicate them in solutions that use snapshots. So that's a given one. Going forward, configure the configuration backups in the NSX manager, move them over to a SFTP site, preferable in another location, and you're good to go. Last one for this is VLANs and external routing. So the devices here is to put your SDDC components like NSX manager on a VLAN-based port group together with all your rest of the supporting techniques, and use a external router, external of NSX in this case, for routing into your management network. And this gives you the ability to always reach your environment in any case if an NSX is not installed, has issues, so it gives you an advantage you always can connect to your system. So moving on to the hypervisor design, a couple of important things here are the NIC choice for your hypervisors. So nowadays, go for a 4-port 25, 2-port 100 gig NIC, and if you do so, make sure it does support Geneva offloading, RX filter, RSS, and those kind of things, and has sufficient PCIe bandwidth to do so. Second one, the advice here is to create a single VDS for a host, attach all the NICs to this host, and in a 4-port design, you can use 2 of them for all your management, backend traffic. So let's say vMotion, management, IP storage, and use the other 2 for tap traffic, uplinks, and those kind of things. You have a good separation there, and it's easy to manage and to change afterwards. So we have that one. So we talked about NIC choice, VDS design, and talking about MTU. Well, the minimum is 1700. Well, normally we would not set anything in between, so go for the maximum 9000. That is easily done, and it prevents all kinds of issues in the future. Another thing for your hypervisor design is that you could do so. You could introduce an dedicated cluster to put your edge nodes on. If you do that, it shows a bit like this. So what's happening there, you can put your NSX Edge Nodes VMs onto this dedicated cluster. So it frees up the resources, and you can fit and tailor-made this cluster specifically for your edge nodes, which can be a big plus. Second one, and what you could do, depends a bit on the situation, is to prep that cluster also for NSX. When you do so, also your overlay segments from all your tenants live there. And if you have, I think a lot of us do, has some form of additional security appliances, you can put them also there. You have a centralized locations for all your north-south, southbound systems. Don't forget to include them in the NSX exclude list. So for else, DFW can do some interesting stuff. So given that, and the last one is customer VLANs. So back in the days, you would probably configure all your customer VLANs on your resource cluster hosts. Well, with NSX, it can be the case, but it's not needed anymore. You can configure your customer VLANs also on this dedicated cluster and use them for example, NSXT uplinks for bridging. You have them all located in an isolated location, which frees up the configuration and makes your resource cluster more easily to manage because it just has its default port groups, including your tap traffic. So it simplifies your environment. That can be a big plus. So moving to the edge cluster design, this one shows a two-side edge cluster. So if you do so, what's an important thing here? If it's a multi-site design, if you configure uplink profiles for them, but different in each location, that way you can use different VLANs on both sides and have different tap pools, and that makes it possible for you as a provider to use routed links between both edge nodes in certain locations. So that gives more flexibility and prevents stretching your networks and your fault domain between multiple locations. So it can be an advantage for all of us. So given that, also important one is failure domains. So if you have a larger edge node cluster, for example 4 nodes for your T1s, be sure to configure the failure domains within the API for these clusters, so you know for sure that if issues arise in your platform, that your T1s in active standby are running great, given the multi-sites you're using them in. Last one, VLAN transport zones. It relates a bit to the previous one. So if you have transport zones, a solution that you could use is that create a VLAN transport zone for every type of traffic. So for bridging, for T0 uplink, or even when you need it on a compute cluster. And if you do so, it frees up again the complexity of your resource cluster, and therefore you make sure that the VLANs are only configured and can be used on the spots you need them. So that's a good thing for simplification and uniformity of your platform. And last one, of course, use transport node profiles when configuring your ESXi host. And these are only available for ESXi, so not for edge nodes themselves. Last one, a couple of things for edge nodes are the size of them versus the performance. So the smallest one to be used in production would be a medium-sized edge node, which supports up to 2 gig of throughput. When you have more services, go further with that, use a large one which is supported up to 10 gig. There is also an X-large one, but it's mainly used for if you have a lot of VPN connections or load balancers, which nowadays would move to RV anyway. So I think there isn't much use for the largest one. And for bare metals can be a very good solution if you have high bandwidth demands. So these can go up to nearly tested up to 400 gigs when having them in the right configuration and have lower latency. But if you do so, make sure that these network cards are supported and the hosts are supported. So that's a thing to know for these. So moving on to your edge cluster routing considerations that are important for us as a service provider. First of all, a bit like Yves mentioned before, a single edge cluster can only host a single T0 router. So that can be enough for a single customer, or maybe for a smaller one. But if you go larger and have more, you want to use multi-tenancy, go for the VRFs. But if you do so, make sure you configure its parent first. So on the uplink side and on the BGP side. Because if you first create your VRFs, you need to delete them all again and start first. So you can get into issues there. The AS number is an important thing I just mentioned briefly in the beginning. So if you create AS numbers like you see on top, you don't have to need the parent AS number in the newest release of NSX, which is 4.1 upwards, and you can use unique AS numbers for your tenants going forward. So that's a big plus on that one. On the T0 upwards routing part, there are a couple of things there. So Yves also already mentioned the differences between inter-VRF routing and leaking, which is not the same. So we'll go from inter-VRF routing from here. And for the scalability and availability part, ECMP and BFD are a couple of important ones. So for your T0s, which are act as an active way, use ECMP for scalability, up to a couple of 8 hosts. That is important. And for the availability, BFD is an important one. So normally it would have a converge time when using it for, around 1 to 2 seconds, which is pretty fast. But the important thing to use is because it can detect issues in the connectivity path. So if you have a switch that the port is up but does not forward traffic, BFD can sense and shut down your BGP session in a very fast way, so prevents you from issues having with your customers. So it's an important one to mention here. The last one on the routing protocol itself. So if possible, use BGP wherever, and go for static only when there are certain use cases to do so. For OSPF, it is there. It can be beneficial in some cases, but if possible, again, go for BGP. And the last thing to mention for static ones, so by nature, it does not detect issues on the forwarding path to your upstream router. So if you do so, use it in combination with BFD for failure detection and fast failover. Else, you could black hole your routing in this situation. And last one in this slide is the separation of your T0 and your T1. So if you're doing that, it makes it possible to scale up or scale out independently your edge clusters for those two, and you make sure that you know upfront where your services are running. The T1s and upstream routing on A, the other ones on B, and it gives you an advantage in your operational model. So moving forward to bridging, in this example, I'll show you a multi-site bridge. What is important to know from this one, that if you create bridging clusters in general, go for a dedicated set of edge nodes. It comes at a cost of just 2 VMs, but doing so, you make sure that this often more latency-sensitive situations where you use it in or higher bandwidth demand are, so you know just for sure that these are used for this situation, and it makes you operational better and has a better quality of service in this case. So when you use a multi-site bridge, again, as a previous example for routing, use different uplink profiles per site to have a routed tap traffic between them. So that's an advantage. And a thing to mention is that the NSX bridge does not have loop prevention techniques. So for example, STP, RSTP, as we know it from the, in networking land, but that is not really needed because it's always an active standby situation. In this case, your passive one does never forward traffic, so you not get into a loop. Other things to note that here is that by default in the segment security profile, BPDU traffic, well, like STP, RSTP, is dropped by default also. The last one from this is the ability to implement QoS policies to prevent noisy neighbors and filling up one of your customers the whole bridge, so we get connectivity issues going forward. So on to the logging part. So this case, I've shown you the current situation, how NSX and VCD do the logging. So you create a log rule label. NSX, VCD does it for you. If you do it in NSX, you need to do it on a per rule base. And it's of course needed for troubleshooting or for compliancy. It's important for you and your customers. So the normal way if implementing these log labels is that it's the DFW firewall logs and the gateway firewall logs, so from the host and the edge nodes, will forward to your favorite log solution, and you can forward it there to your customers one, recognizing because of these rule log labels. So the new way in NSX multi-tenancy, so on a project and or a VPC configuration, the admin defines a so-called short log ID. And this log ID is implemented in every firewall rule created in these constructs. So in this case, it will be implemented in the project or in the VPC as a whole. And that's an important one for people going into NSX directly, but it wasn't really able to do so before the 4 version. So while doing so, it is still the same for DFW and gateway, so you get a consistent logging. And secondly, the security and audit logging, which you did not have before, is now able to log to your log solution and forward to the customer. So I think that's a big plus for this situation. So a couple of examples, and let's stitch it together. So in this case, we have tenant orange and tenant green on that side, and an ISP in the middle. So how can you configure it together? So in this case, there are a single edge cluster, so node A and B, put a VRF on top of it for these customers. And upstream routing is configured, so that way they can configure have connectivity to the WAN. And for us as a service provider, in this case, a possible way of doing so is create a internet VRF and use inter-VRF routing, which make use of route maps to import or export routes from the central one to your tenants. So that way you can use public IP blocks and those kind of things for your customers. And a default route, of course. So this is a more scalable, robust approach going forward. The last one, if you have shared services as a provider, for example, managed backup, those kind of things, it's not a way of doing so. It could be to connect them also to the central router and export using route maps into your customers who need these services. So that's a way of doing so. So last one, so how to stitch it together from the tenant perspective. So in this situation, we have a tier 1 for customer green on this side, and on the opposite side. So what is happening here on top? There is the same T0 VRF for customer green, and this T1 on this side has a public IP connected. So for this VM here at the bottom to connect to the internet, it can use SNet to go outside, which address is translated, and connectivity is there. Of course, if the firewall rules let it to, and if this VM on the left would need to connect to the customer's WAN, you can create a no-net rule, and traffic flows to the WAN of this customer. So that can be done either way. Additional, there is a bare metal server in the middle that needs to connect for this tenant. So you can create a bridge on a separate bridge cluster that you see here. And so node G and H versus ENF for the T1. This way you can extend this layer 2 network to the VM. You can even firewall on it, and that's the way going forward. So on the other side is a bit of a different situation there. It's also a T1, but this bare metal or third-party security appliance is connected to the service interface of this T1. While doing so by creating a static route and using the service interface, which is supported by Cloud Director in the 4X versions, the VM on the right can connect via the T1 to the appliance, and traffic is happening. So if you can close it up.
Sure, yeah, so quickly, because we're running out of time. So just to kind of recap a bit. So again, NSX topologies, they are logical, totally independent of the physical network. All network functions inside NSX are totally virtualized and software defined. Make sure you look at the design guides and all the validated designs as well. We have this provider and tenant separation. And multi-tenancy is already built in NSX today, or you can leverage Cloud Director, of course, for this. With that, here are some links as well. You will get those PDF slides, some links to other sessions during Explore, the design guides as well. Please get in contact with us if you have some more questions. And please make sure you take your survey. And also, if you have any questions, you can stay here in the room because we're actually the last session. So feel free to stay here, and other people who have to go, have a great rest of the day. Yep. Thank you.
Thanks all for being here.